Hello, my name is Nelly, and I'm speaking to you from Singapore. So, if you're listening to this pre recorded talk, then let me begin by thanking you for showing interest in our work and coming by to listen to this talk. Our work is concerning this quantity, which is the variance of relative surprisal, and we call it for short the relative variance, and we studied this from the single shot perspective. So this is joint work between the three of us. Paul Boas, who is finishing his PhD in the Free University of Berlin, and myself, who has recently moved from Berlin to NTU Singapore, and Hendrik Wilming, who is currently a postdoc at ETH Zurich. And this work actually grew out of close to 2 year conversations and working together to understand the properties of the relative variance. So let me begin by making a small advertisement, if you don't mind, that I'm starting out to build my own group in Singapore, and I'm on the lookout for PhD students and postdocs to come and work on topics of quantum information with a focus towards applications in quantum thermal and many-body physics. So for PhD students, the intake would start in August next year, and if you are interested, please write to me. So let's begin. And I will first begin the talk by identifying three regimes of information processing. So first of all, there is the asymptotic IID limit, where we are concerned only about the limit of infinitely many copies, and in which case the relative entropy and the corresponding von Neumann measures has been extremely central. So that they have been shown to characterize almost everything about rates of both classical and quantum information processing. So for the large but finite n scenario, which is also pretty realistic assumption in certain cases, one can then characterize deviations from the infinite copy case by higher order corrections, in which the second order quantity, which is the relative variance, is then found to be a meaningful quantifier for such a regime. Then there's the single shot regime, where we don't make any assumptions about the structure of the distribution, so we are ultimately targeting statements that you can make concerning a single run of the process. I think this is also a central topic in the Beyond IID community. So in this regime, if we look at specific tasks, such as cryptographic security, then maybe only the min or max relative entropy becomes relevant. But for general statements about the feasibility of state transitions, usually the statements would involve the joint collective description of the entire family of Renyi divergences. And this makes the single shot regime hard to analyze because of its lack of structure, and that applications to problems would usually also require further optimization. And moreover, we know that in the quantum regime, there exist non equivalent ways of defining the Renyi quantities. So recently, there have been some interesting work in developing the significance of the relative entropy in a single shot regime. And this happens when a catalyst is allowed to be correlated with the system of interest. So, a natural question to pursue is then perhaps whether the relative variance has any operational significance at all in the single shot regime. So, on the other hand, we also know that all these quantities, the relative entropy, the relative Renyi divergences, they are monotones with respect to resource theoretic type of free operations. And this is a feature that holds in generality across different RT frameworks. So similarly, one might ask, does the relative variance also have a role to play in such a scenario? So by studying the properties of the relative variance, we make a first step into answering these two questions affirmatively. And I say that this is a first step because we develop these results only for the special case of semi-classical states, in other words, when rho and sigma here commute. And this means that we can address two particular scenarios, the case where the reference state is the maximally mixed state, or the case where we have a generic sigma, but the statements would be then limited to a subset of states rho, which commute with sigma. So although, of course, the first case is a special case of the second, we are listing them separately here because they imply results for single shot transitions under two different types of frameworks of interest. So I guess most of the Beyond IID community would know the quintessential scenario of resource theories, namely to define a set of free channels and asking for the state transition conditions that inform us about how a state rho can be transformed into another state rho prime. Very often, the state of free channels are then those that preserve a state or a set of states, in other words, the maximally free operations. And all our results in this work concern state transitions under such channels. So case 1 then studies the transformation of arbitrary states under the set of unital operations, which we know is actually fully characterized by majorization, but in our work we also study approximate transitions. While case 2 allows us to study generic sigma preserving channels, but then here our results hold only for states which are incoherent with respect to sigma. And then we use these two notations here to denote the existence of a sigma preserving channel that performs the transition or the epsilon approximate transition. So before we go into the results, we thought that it might be useful to quickly summarize what we learned about the relative variance along the way, because we believe that these technical properties are of further interest to the community. So let's start with the easy ones. We have additivity under tensor product, we have non-negativity, which have been long known. In this work, we prove a uniform continuity bound for the relative variance. We can prove that the relative variance is subadditive up to a correction term that depends on two things. It depends on a constant k, which is a function of the dimension, and also, I think, of sigma. And a second term, which depends on the mutual information and vanishes as the mutual information goes to 0. So next, we also know that when sigma equals to identity, we know that the variance is 0 for particular states, and these are known as flat states because they have then a flat probability distribution. And lastly, we also found out that it is known how to explicitly find a state that maximizes the non-relative variance, namely when sigma is equals to identity. And this was actually derived in a paper by Reeb and Wolf, while they study second-order corrections to the Landauer's principle. In this work, we present three main results. And the first result is that the relative variance plus the relative entropy jointly gives sufficient conditions for single-shot approximate state transitions. So let's recall that in the IID scenario, we know that approximate transitions with vanishing error are fully governed, actually, by the relative entropy, and this is due to asymptotic equipartition. So what we show here is that for the single-shot scenario and for an arbitrary amount of error, we have sufficient conditions which derive from the relative entropy together with a correction term that depends on epsilon and it depends on the relative variance. So the proof of this theorem rests on the stronger statement that we developed for bounds on Lorentz curves. And with the same technique, we can also derive clear bounds on how much the min and the max relative entropy deviates from the standard relative entropy. So although these bounds are far from tight, they are nevertheless simple conditions which are useful in their own way. So let me quickly point out two simple applications. And the first one consists of an upper bound on the error that we can afford to make in state transitions. So this is simply a rewriting of the theorem that we have before. And now if we take the IID limit, then the upper bound would go to 0 directly. So When we consider these bounds applying to finite but large n setting, then we can derive also second-order corrections to the rates of state transitions. And these statements are similar to the work done by Camille, Chris, and Marco on second-order corrections. Their bounds are much tighter in general, but ours are achieved with simpler methods and simply by applying our theorem and solving quadratic equations. What's more, we can also recover the resonance condition that these authors identified when second order correction terms vanish. So we capture this essential and interesting feature in the large but finite n regime as well. So another application that we have is when we look at non-IID but so-called ergodic states, which happen in generic spin chains. And Philip Weiss will be talking about this later in the conference. But in essence, these are states where correlations would vanish with increasing distance in lattice between lattice sites. So using our result, we can then establish a very direct proof of how such states are interconvertible with each other, and the rates depend exactly, again, on the relative entropy, again, with vanishing error. So this first result kind of allows us to conclude in very simple and clear way that the relative variance comes indirectly as a measure of sufficient conditions for state transitions. And in particular, the smaller the relative variance, the less overhead is incurred onto single shot processes due to finite size effects. For example, if I look at this upper bound of the error, the smaller the variances are, it means that we can afford to make smaller errors we can achieve the state transitions with even smaller errors. So maybe then it's natural to ask whether we can decrease the relative variance under free operations. So one can easily come up with immediate examples where the relative variance is not a monotone. So however, when jointly considered together with the relative entropy, we can make some interesting statements about monotonicity. And this is our second result, which is that we find a new monotone that depends on both these quantities, the relative entropy and the relative variance. So this is the function that we derive, and this is a resource monotone. And for the special case of sigma equals the identity, this reduces to a corollary that gives us a Shaw concave function, which was previously not known. And here we plot, given just a very simple three-dimensional system, the set of given, for example, an initial state, we have the set of states which have a partial order that are majorized by the state, and we also have the m increasing states and the entropy increasing states. So from these graphs, we can see that although both the relative entropy and the function m are Shaw concave, the decrease of our new function does not automatically imply the decrease of the relative entropy. So they are genuinely different monotones in that sense. So an application of this monotone is that we can use this to study the problem of entropy production, which is usually only discussed in the case of sigma being identity and having unital channels, or thermodynamic type of scenarios. So since the relative entropy is a resource monotone, we know that for sigma preserving channels, for these kind of processes, if we look at the quantity delta S, which is the difference between the input and output relative entropies, then we know that this quantity is always non-negative. However, due to our new resource monotone, what we can derive is actually a stronger positive lower bounds on the change of this quantity delta S, and this is dependent on the change of the relative variance. So in particular, if we consider processes that try to decrease the variance, then this necessarily leads to a proportional decrease in the relative entropy, which we recall is the unique relevant quantity that determines the worth of a resource state in the IID limit. So we can extend this result to consider not only free channels acting on a single system, but also the dilation of such channels when we consider a larger environment, here modeled as B. So in particular, consider the dilation of this channel being a sigma AB preserving channel and acting on initial states rho A and rho B being product. So now we know that by superadditivity of the relative entropy, that if we look at the sum of local changes in the relative entropy, then we see that this quantity delta SA plus delta SB would be non-negative as well. And this is the property that we call local monotonicity. Our theorem on entropy production can then be generalized as a function of local changes on the relative variance. So in particular, again, we find that the sum of relative entropy change is lower bounded by the sum of relative variance change minus a small correction term that depends on the mutual information. Okay, and we have explicit forms for the constant k and the function f, which you can check out in our manuscript. And now one may ask, well, how do I know if such a bound is even interesting at all? And the thing is that many resource theories require special types of such ancillary systems, such as batteries or catalysts. And because the system A and B here that we have are arbitrarily finite dimensional systems in this construction, so our results can be then applied to study such scenarios without having to explicitly analyze the correlations between the systems. So let us make a simple case study to see what this result tells us by considering the scenario of correlating catalysis. Okay, so this considers the special case where we study the use of a catalyst under unital channels, which means that the local state on system B stays the same. And in a very early slide, we mentioned that this is the scenario where the operational significance of the relative entropy is found in the single shot regime. In other words, it's known that state transitions induced on the system A are possible as long as we have that the change in relative entropy on system A being non-negative. But this result actually assumes that we have access to all possible catalyst states on B. So in other words, this result is completely silent to the question of, how large the catalyst actually needs to be in order to actually perform this process. Now, if we were to apply the result of our theorem here, then first notice that we are in the scenario where delta S on B and delta V on B are both 0. Then what we find is from the corollary that if we write this out and we take away the contributions from B and a rearrangement of these terms, picking out basically massaging a little bit on these bounds allows us to relate the change on variance with the change on relative entropy in this way on a term that depends on the dimensions of the systems. And what this tells us is that now if we fix the dimension of A, and if we also fix the change in relative variance on A, then the smaller delta SA is, which if you only slightly try to do a transition that slightly only change the relative entropy, then the larger the amount of the dimension of the catalyst has to be in order for this process to actually happen. So this makes a statement then about what is the dimension of the catalyst required. So let me take a quick interlude to repeat that the derivation of our results required us to develop certain technical properties of the variance. And the first one is corrections to subadditivity as a function of mutual information. And the second one is concerning uniform continuity of this quantity. The derivations were very technical, but it would be nice to be able to find simpler ways to maybe strengthen these bonds, because right now they would only hold for sigma states of full rank because they diverge with the smallest eigenvalue of sigma. And this is not so nice. But let us go on to describe the last result of our paper, which arises from this bipartite scenario. So we see that the sum of this local changes of relative entropy is non-negative, even for multipartite systems, which we coin this term as local monotonicity. And this is mainly a result based on superadditivity of the relative entropy. So it does seem like a nice property, especially when we are talking about studies in physical systems where the local observables are of central interest. And our third result is actually a clarification that local monotonicity by itself is actually unique towards the relative entropy. So it's a really special type of quantity. The formal statement is that if we look at the set of full rank states, and also if we look at the set of channels that map full rank states to full rank states, then we can ask for a function that satisfies local monotonicity with respect to these channels. And this requirement itself uniquely singles out the relative entropy. So we realize that this is extremely relevant for physics because it is an explanation, for example, for a version of Boltzmann theorem. So Boltzmann sets up a particular model of interest to describe thermodynamical kind of interactions and derive his H theorem. So in this setup, he considers a set of independent particles, and at each single step, two particles would interact with each other. Whereas subsequently, what happens is he invokes this Stoßzahl-Ansatz, which is or known as the molecular chaos assumption. And he assumes that the correlations between these two particles is then subsequently lost. So if we were to find a function of such a model that is monotonic with respect to time, then this function actually now uniquely singles out the von Neumann entropy or relative entropy. So with this, I conclude the overview of our work. We had a lot of fun and actually a lot of pain in studying this relative variance because it's not the most easy quantity to bound. And I think it's reasonable to conclude that we have understood it in a much clearer way than we started in terms of its significance for single-shot processes. And I think, as usual, there are open questions. The first being whether any of our results and observations can be derived also for the fully quantum case. I suppose it's probably going to be true, but we have only used a very classical approach towards this problem with dealing with probability distributions and majorization. And another point to make is while the continuous parameter Renyi family has been kind of the main entry point for single shot effects, we wonder if the hierarchy of higher order moments of the relative surprisal can be fully further developed so that it gives us a complementary perspective of processes which are beyond IID. So, for example, one possible aspect of this is to understand how the higher moments can allow us to construct increasingly refined Shor concave functions or monotones, such as when the single shot effects become more pronounced. So I think this is it. And once again, I want to thank you for tuning in. And given that we cannot take questions live, I also want to invite you to write to Paul, me, and Henrik if you have further questions or remarks that you want to share about our work. So that's it. It's a tremendous pleasure to speak, and I do hope that you enjoy the rest of the conference. Thank you.